Well, it looks like we're live again for video 3 of chapter 3. This will be 3 of 3. This should be the last video, I hope, for chapter 3. We'll pick this up on pole foundations. Chapter 3, page 22 of chapter 3, or section 22 of chapter 3. Pole foundations elevate the timber structure above the ground plane. Required um, minimum excavation and preserve the natural features of the existing drainage, or it provides for storm surge like on the beach, on the Gulf Coast, or along any beachfront property where you have potential for hurricanes and a high storm surge. Hopefully your pole structure is up high enough that the storm surge does not flood it, and that the pole structure is strong enough and is embedded deep enough that the crashing waves and water doesn't overturn it. Um, we know what this kind of bracing is. That's X bracing. This is lateral bracing. Um, Poles are spaced 6 to 12 feet apart, depending on your soil condition and your engineer and how deep they are. Um, they can have insulated floors. Um, Solid built upper space wood beams. You can read all of this. I expect you to. Um, so let's see what this has for us in pole structures. And of course, the poles are treated. Um, okay. All right. Floor should be designed and constructed as a diaphragm. Now, why is that? Well, we know what a diaphragm does, right? It stiffens the structure. Since these poles are spindly, um, and they're like straws stuck in the sand or the soil. When the wind blows, um, that floor needs to be a structural element for a diaphragm, just like the walls do. So the whole box needs to be a structure, including the roof, as much of a rigid connection as you can make these, and that way this whole thing is stiff, as stiff as it can be for torsion and for lateral forces. All right. He gives you some rule of thumb from 5 to 8 feet. I would not trust this at all. Um, you use your soil engineer and your structural engineer's advice for this. Um, this might work, it might not work, depending on the type of soil, depending on how much rain you get, how much runoff you get, and how much erosion is going to take place over the life cycle of this structure. Um, Especially something this steep, I would put some sort of water diversion concrete riprap, high stuff to slow that water down and divert it away from my structure if I could, if it wasn't running on somebody else's property. Again, your mileage is going to vary. This is all based on your soil mechanics and your structural engineer's advice. All right. Okay. And it depends. Are you in a seismic zone? I guarantee if this is in Colorado, in New Mexico, Colorado, out west past the Great Divide, you've got seismic stuff to worry about, um, especially in California. Um, what you have to worry about on the Gulf Coast is you don't have a slope like that on the beach, but you got tidal surge and tidal and wind and wave forces. So the local ordinances and the codes will govern. All right. There's different ways to connect the structure to the poles. You can notch them. You can use clips, whether they're called spiked grid connectors or gator clips or bulldog clips. Um, if you're going to use these clips, they're good for making sure this stuff is level and a temporary hold. And you're still going to need to drill through there and bolt them. And I would, if I was your engineer, make some sort of try to make as much of a rigid connection as I could out of out of this wood beam to a wood pole structure. Um, you can gusset it. These verticals or gussets. Um, I've seen a lot of these with steel, using steel gussets, not wood gussets. A steel plate is through bolted through the bottom and then bolted through the top, and these would be steel. Um, so I would certainly take you the advice of your structural engineer. The problem with this kind of detail is you've got your pole sticking up. Um, Now, if you're going to use the pole, the exterior poles, as taller poles to support a porch roof or something, that might be fine, but it's going to be difficult to get your floor diaphragm through there, right? Here this can be your whole floor diaphragm. But again, these notched gussets, I would not use wood. I would use structural steel plate or channel, steel channel. All right, this is a description of the grade. Your treated wood poles theoretically would then come down and rest on a reinforced concrete pad. That's assuming you can dig down or bore down and pour this and actually embed galvanized metal straps for better anchorage. Now, down on the Gulf Coast, they drive those piles into that sand or vibrate them down into the sand. Some of the more expensive ones that I've seen, they use steel pipe and vibrate those down through the sand at a specified depth, and then fill the interior with reinforced concrete. Then the connection is much easier than wood. You can weld and embed the concrete anchors into the hollow steel formwork before the concrete hardens as you're pouring it. This shows a concrete collar and crushed in damp soil. This would be in an area where you had a pretty good soil condition, not nasty sand down on the Gulf Coast. Again, he makes a mention of a frost line here that goes back to your area, wherever you are on the planet, and the soils report. They put sand in this one, and they poured a concrete ring with spikes in the lag bolts or spikes in the wood timber post for anchorage into the concrete, and then they finish backfilling. And this one is just backfilling with concrete or soil cement, which is stabilized sand. It's cement stabilized sand is what it is. We use a lot of cement stabilized sand in sewer construction down here in this area. It hydrates and gets hard. So that's what these three determine. Is anyone better than the other? It depends on where you are. Depends on what your engineer recommends and your soils engineer recommends. All right, deep foundations. What is a deep foundation? Well, that kind of depends on where you are in your definition. You know, I told you that shallow foundation, deep foundation. What does that mean exactly? Deep foundations extend down through unsuitable or unstable soil. Okay, well, that's fine. That's fair. To transfer building loads to a more appropriate bearing stratum. Again, that depends on your your soils analysis, right? Those deep cores that you dig. All right. So here's some examples of how to do deep bearing stratum. You want to go to rock or dense sands and gravels below the superstructure. Two principal types of deep foundations are pile foundations and caisson foundations. A pile foundation system of in-bearing or friction piles. That means they're just driven like a nail into the dirt, okay, into the soil. Caissons are usually drilled and then filled with concrete, okay. And then on top of the foundation and the substructure is then your load-bearing wall. And here are the details up here for all of that. Now a cap, or what we would call a foundation pad that's on top of piles, is called a pile cap. And these are some examples of pile cap layouts. Your mileage will vary depending on where you are on the planet and what are the common details and expected engineering requirements by your structural engineer. Okay. All right. This is an example of a column coming down to the pile cap or the foundation pad. Here is a load-bearing wall that comes down below the subgrade. So part of the wall is below the subgrade onto the pile cap. So this much of the wall needs to be what? It needs to be waterproofed, right? Piles may be of treated timber poles, but for large buildings, you'll use giant steel H sections. Our concrete-filled pipes are precast, reinforced, or pre-stressed concrete. Some piles are driven in by a giant hammer on the top of a crane. Some are vibrated in, depending on the type of soil that you're trying to push the piles through. Some have to be drilled, and then the steel pipe are pushed down through the hole and vibrated through the hole, and then filled with concrete. There are all many different ways of getting these in, okay? Steel H sections, if you're going to drive them in the ground, they'll be driven in the same way as sheet piling or regular timber piers, timber piling. Will just be driven till you get a certain resistance. And normally what they do is they count the number of hammer hits on the pile. When they get to a certain depth, that it takes X number of blows of the steam hammer, the air hammer up above, to make the pile move so many inches. Then based on the soils analysis and the soils engineer calculations, they'll say, okay, that's good enough. And then they'll switch over and start driving another one. And so generally there's somebody standing out there counting the number of hits per pile, and they've got a chart, and that goes into a inspection report. All right. And it's basically friction, just like a nail in a piece of timber on these things, if they're friction piles. Now, if they're going down to bearing stratum or solid rock, these are bearing piles. So let's say we drilled these caissons down all the way to rock, inside the rock, and drove then hollow steel pipe down there, or they drove H piles until they hit the rock, and then they filled this with concrete, or if it's an H pile, they just left it. All right. Timber piles are logs driven usually as a friction pile, like a nail driven through a piece of wood. Sometimes they have to put a steel shoe on the bottom to keep the pile from getting all beat up while it's being pushed through the soil. Sometimes the steel shoe's got a point on it, depending on the soil. An H pile is just an H beam, so it's like a steel nail being driven into the ground. Hollow tube is just that, a big piece of hollow pipe. It may need to be drilled after it's driven, or you're drilling an undersize hole and then driving this and then cleaning it out with a clean out drill. And it talks about that over here. Precast concrete piles, round or square or polygonal cross sections, and they can be pre-drilled and then driven. Most of the timber piling that we drove, all the timber piling that we drove at the 69th Street wastewater treatment plant clarifiers to keep them from popping up because Buffalo Bayou was right next door. When they were being drained and cleaned later on, were all pre-drilled. They would pre-drill a hole and then drive the pile down through the pre-drilled hole. That was all designed by the soils engineers and blessed by the structural engineer. So generally what will happen, you'll see these pile drivers, they'll have an auger off to the side where they'll pre-drill the hole, and then the pile will be drug up underneath the hammer. The hammer's then dropped, and then they start driving it into the ground. Cast in place concrete piles are constructed by placing concrete in a shaft in the ground. You normally drill and sink a caisson or form, and then you pour concrete in it. Okay, that's a cased pile. Uncased piles are constructed by driving a concrete plug into the ground along with a steel casing until it meets the required resistance, and then ramming concrete in place as the casing is withdrawn. So you withdraw it and you're filling it full of concrete. Here's some examples of the process of that. Most efficient are the cased piles. In this, the uncased, you get to reuse the casing. Micro piles are high capacity, small diameter, usually 5 inches to 12 inches. They're drilled and grouted in place, and then the piles are typically reinforced. So, and they're used for underpinning and mostly for emergency repairs. Again, this goes back to fixing something that shouldn't have been designed better in the first place. You really don't want that around much vibration, because this is very expensive. This is after the fact, and that means you got to excavate down to a certain point so you can drill these down. And in this case, it should have been either one of these or one of these piles down here on the good stratum for the bearing. Normally what will happen is they will dig down to the footing off to the side enough to try to tap into the existing footing after they drill these. And then they'll surround this whole square footing with a reinforced square footing that they drill into the side of it and try to underpin all of this. And sometimes they might actually be able to go into underneath the footing with some structural cribbing. But this, again, this is very expensive. This is after the fact. This is to fix something. This is very expensive. This is expensive, but this is like doubly expensive. So you really want to get it right the first time around, because generally this happens after the building's built and you've got differential settlement, like we saw in a previous image. Caisson foundations. All right. Caisson foundations are cast in place, plain or reinforced concrete piers formed by boring with a large auger are excavating by hand. I don't know anybody who excavates this stuff by hand anymore. A shaft in the earth to a suitable bearing stratum and filling the shaft with concrete. For this reason, they're also referred to as drilled piles or piers. Nobody hand does this. Um, these things are drilled, and like I showed you with that ugly sketch I made, this is the last step. This bell bottom down here. The blades are in a can that attach to the auger shaft. After the main shaft is drilled and the caissons drop down in place, now if the soil it will hold up and won't collapse long enough for them to get the concrete in there, they may not need to use a casing. But a lot of times they do, or they'll drop sonotubes in there, and they just stay in the ground with this stuff. And then the blades are inside this box, inside this cutter. And when it spins, these blades sling out, and they make the shape of the bell bottom. And then they're brought up, and augers drop back in again to pull out the left of the dirt, and then they drop the reinforcing cage down to a specific area, a depth. And sometimes the steel cages are really deep, sometimes they're shallow, depending on the soil conditions and the bearing and the structural engineer. And then they're cast and above the topography, and then the rest of the structure is put on top of it. Okay, so this is the caisson, this is your reinforcing steel, and this is your boring. It's a temporary casing, or it can be a permanent casing, depending on the requirements of the soil that you're digging it in. If this area in here that you're trying to get through is very granular, then you'll drive a casing in there and then clean that out, because you don't want the hole to collapse while you're getting the concrete in there. This is the base of the caisson, or the drill pier, a bell shape, so that you can spread the load out. And they can be anywhere from 60 degrees to 45 degrees, and to a suitable bearing of soil or rock. And a socketed casing are drilled into a stratum of solid rock in order to gain additional frictional support. In other words, they'll drill down into rock. We don't have that luxury down here because we don't have rock underneath us. Up north, on some of these super high buildings, they might do that. Okay. Rock casings are socketed casings, but have a steel H-section core within a concrete-filled pipe casing. So they drill down through the rock, and they drop the caisson down, and then they'll put a big H-pile in there, structural steel shape, and then fill all that with concrete, and then start putting the building on top of it. So that ends chapter 3, believe it or not. And how long is this video? It's 23 minutes, so it's about half of what the normal ones are. So if you have any questions on chapter 1, 2, or 3, email me. And this ends the first 2 weeks of video lecture. I know some of this was probably painful to listen to. Again, don't worry about the exam, which is going to cover chapters 1, 2, and 3. Again, this is an 8-week class, and we don't have the luxury of dragging this out over 16 weeks. So I wouldn't worry about it. You have the book, and it's going to be open book test anyway. It's an online class. How can I not make it an open book or open internet test, right? So anyway, if you have any questions, send me an email, and we'll see you on the next one. I'll start making the other videos, and we'll see where we go from here. We may all need counseling. Those counseling services in that syllabus after this is all over. Well, anyway, all right, well, next one. Bye-bye.